Welcome back. In this tutorial, we will simulate a half-wave Thyristor rectifier using MATLAB Simulink. Problem statement. Simulate a single-phase, half-wave Thyristor rectifier circuit, and observe the output current and voltage waveforms at different firing angles. Getting started. So, let's get started. Launch Simulink and create a new model. Save the model. Add the required blocks. Open the Simulink library browser, and then launch the standalone library browser. Go to Simscape, then Electrical, then Specialized Power Systems, then Sources, and add an AC voltage source to the model. Next, open Power Electronics and add a Thyristor block. From Passives, add a series RLC branch. From Sensors and Measurements, add a multimeter block. Also add a Power GUI block to the model. Now go to Simulink, then Sources, and add a Pulse Generator block. From commonly used blocks, add a Demux block and a Scope block. Block configuration. Let's arrange the blocks. Double-click the AC voltage source to open its parameters. Set the peak amplitude to 311 volts, the frequency to 50 Hz, and under Measurement, select Voltage from the drop-down menu. Click OK to save the settings. Open the Thyristor block and disable the measurement port. Select the series RLC branch, press Ctrl+R to rotate it, then open its parameters. From the drop-down menu, select R. Set the value of R to 10 ohms. Under Measurement, choose Branch Voltage and Current. Double-click the Demux block and set the number of output ports to 3. Open the scope. Click the gear icon, set the number of input ports to 3, and click OK. Next, click View and adjust the layout. Let's also change the scope style for better visualization. Right-click on the first display. Select Style, and adjust the colors as needed to enhance visualization. Right-click on the first display, open Configuration Properties, and set the title to Source Voltage. For the y-axis label, type Amplitude. For the second display, assign the title as Load Voltage. For the third display, set the title to Circuit Current. Open the Power GUI block, set the simulation type to discrete, and reduce the sample time to improve accuracy. Make the circuit connections. Open the multimeter block. First, select the AC source voltage and press the Select button. Then, choose the branch voltage. And finally, select the branch current for measurement. Open the pulse generator block. Since the supply frequency is 50 Hz, the time period will be 1/50. Enter the firing angle in seconds. For a firing angle of 0 degree, enter 0 divide by 360, then again divide by 50, because the time period is 1/50 seconds. In degrees, 1 cycle is equal to 360 degrees, and in seconds, 1 cycle is equal to 1/50 seconds. Go to Simulation tab, set the simulation time to 0.08 seconds, and click Run to start the simulation. The resulting waveforms match those of a half-wave diode rectifier. At a firing angle of 0 degree, the half-wave Thyristor rectifier operates identically to a diode rectifier. Now, let's set the firing angle to 30 degrees and observe the results. In this case, the output voltage and current in each cycle is delayed by 30 degrees, and conduction begins only after this point in each cycle of the input. This phase delay occurs because the Thyristor remains in the off state until it receives the appropriate gate pulse, which is applied at the specified firing angle. Now, let's set the firing angle to 90 degrees and observe the results. At this point, conduction begins only after 90 degrees of the source voltage waveform. Next, let's set the firing angle to 180 degrees. In this case, the gate pulse is applied exactly at the beginning of the negative half cycle. However, since the anode is negative with respect to the cathode, the thyristor is reverse biased. As a result, the thyristor never turns on, and in theory, the output voltage should be zero. In practice, however, we still observe a very small output voltage in current. This occurs due to the presence of the snubber circuit, which allows a small leakage current to pass even when the thyristor is in the off state. As you can see, the amplitudes of both the output current and voltage waveforms are negligible compared to normal conduction. Let's verify that no current is flowing through the thyristor, and that the conduction occurs only via the snubber circuit. First, open the thyristor block and enable its measurement port. Next, add a bus selector block from the Simulink library. And connect it to the thyristor's measurement port. Double-click the bus selector block, remove the default signals, and select thyristor current. Now, bring a scope block from the library. And connect it to the output of the bus selector. Run the simulation to observe the results. The waveform clearly shows that the current through the thyristor is zero, confirming that conduction is happening exclusively through the snubber circuit. Now, let's modify the circuit to observe the effect of an inductive load. Replace the purely resistive load with a series RL load, since in practical applications most loads are inductive in nature. Set the inductance value to 10 mH. Next, set the firing angle back to 30 degrees. And run the simulation. You will notice that the inductive load smooths the output current waveform, reducing its sharp transitions. However, it also introduces negative spikes in the output voltage due to the energy stored and released by the inductor during each cycle. Now, add a freewheeling diode across the load to eliminate these negative spikes. Run the simulation again. You will observe that the negative spikes in the output voltage are now completely removed. To clearly observe how the thyristor responds to the gate triggering pulse, let's display the triggering signal on the scope as well. Open the scope block and increase the number of input ports to 4. Then adjust the layout for better visibility. Right-click on the fourth display panel and assign the title Triggering Pulse. Next, connect the output of the pulse generator block to this input of the scope. Run the simulation. You can now clearly see the relationship between the triggering pulse and the corresponding changes in the output waveforms. Summary. In this tutorial, we successfully simulated a single-phase half-wave Thyristor rectifier circuit in Simulink MATLAB. We analyzed how varying the firing angle affects the output voltage and current waveforms. Your task: 1. Measure the average output voltage at different firing angles. 2. Observe how the average output voltage changes as the firing angle increases. Please answer the following questions as well. 1. What happens to the conduction period of the Thyristor as the firing angle increases? 2. Why does the average output voltage decrease with an increasing firing angle? 3. What role does the freewheeling diode play in protecting the circuit and improving the waveform? 4. How does the triggering pulse influence the exact start of conduction? 5. Can you think of real-life applications where controlling the firing angle of a Thyristor is useful?